Hey, I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life.
Okay, Jam, we have talked about baking soda, also known as sodium bicarbonate, many times before.
That's right. Yeah, we have.
And today we're going to talk about how I didn't misrepresent, but how there's a gray area to baking soda.
Interesting. Even though it's white. Huh.
Usually we talk about it as a base,
Uh-huh.
It's like a base and it'll react with an acid to produce carbon dioxide and water.
Right.
That's the volcano reaction. That's why cakes are fluffy.
Right.
There's even a derivative of that carbonate in our sparkling water that makes your beverages carbonated.
Right.
Yes. So we have had a lot of conversations around this, but we have not explored one little area of baking soda, and that's what we're going to talk about today.
Okay.
And I'm pretty hype about it. I love finding chemistry that's like, oh, this is an everyday life thing, but here's a subtlety that we haven't looked at before, you know?
Yeah.
So what we're going to talk about, I guess our listeners already know because they can see the title, but you don't yet.
I don't know.
Yesterday, we had like a weird smell in my fridge, and my husband put a little bowl of baking soda in there to neutralize or trap, quote unquote, neutralize or quote unquote, trap the odors.
Right.
Have you heard that before?
I have, and we have a thing of baking soda in our fridge right now.
Okay.
For that exact reason.
Do you think it works?
I don't know if it does or not.
Do you have questions about how it might work?
Yeah, I guess so. I've also wondered, like, how long could, one amount of baking soda stay in the fridge and keep doing its thing before you'd need a different kind? Because, like, we have some in there right now. I'm not sure how long ago we put it in there. I'm like, is it still helping, or should I change it out? Or did I just, like, stir it up or something? I don't know.
Maybe stir it up. Yeah, that's a good question. We can explore that at the end once we've talked about what's happening with it.
But I know that, like, even baking soda companies or whatever, on the package, it even says things like, if you're going to put this in your fridge, you can do this and that and this.
Uh-huh.
And so it's like they know that that's a way people use it. But even then, it's actually not really described how it works, of course. It's just they're assuming that you might want to try that. So I feel like it's one of those tricks that we've all just kind of accepted that we think it works.
Mm-hmm.
And so we just do it.
Well, it probably does work.
Okay.
He was like, oh no, I'm about to get trapped.
I was like, man, that's just been sitting there doing nothing. Just placebo effect. But also, it seems like that wouldn't work for a smell because you'd know if it's gone or not.
Yeah.
So I don't know.
Yeah. Maybe you just like actually have a really clean fridge and you're just assuming it's helping.
Right.
Okay. So here's the thing. We've always talked about baking soda acting as a base before.
Right.
And, when you put it with an acid like vinegar, it does the bubbling thing. And so we're like, baking soda is a base. It has a pH that's in the basic range. It's basic.
Yeah.
But there is kind of a gray area around this where it's not always a base. And we don't really talk about this a lot, I feel like, in our conversations or even really in classes. Like in classes even, I think baking soda is still kind of considered a base. And it's also called sodium bicarbonate if it's paired with sodium or sometimes just bicarbonate or hydrogen carbonate. Those are all options that it could be called. So we don't really talk about this gray area very much. But we're going to talk about it today.
Okay.
But to talk about it, I think we have to go all the way down to the subatomic level and think about the structure of atoms.
Okay.
Are you ready?
I'm ready.
Okay, so most atoms consist of three major parts. Do you know what they are? Listeners at home, see if you can get them too.
Protons.
Yep.
Neutrons. Those are together.
Okay.
Right? Clumped together.
I think so, yeah.
And then the electrons are is a sort of field around.
Like a cloud.
Like a cloud.
Yeah, it's more like there's a high probability of the electrons being in this area, So
right.
It's sort of like an area where they mostly hang out.
Right.
But just like clouds, there's a lot of empty space too.
Were those the three parts you were looking for?
Those were the three parts I was looking for. But now I want to know if you know the charge on all those things.
Neutron, neutral.
Nice.
Proton positive,
Yep.
electron negative. My middle school chemistry science person teacher, Mr. Wise, would be pretty glad because I think that's probably the first that I remember learning that stuff.
Thanks, Mr. Wise.
Is that, I'm assuming that's correct. That hasn't changed, right?
Yeah, no, that hasn't changed.
Since whenever that was, early 2000s.
Those are still the same.
Okay.
I do always take issue that it's like protons, positive, neutrons, neutral. Why aren't they negatrons? Why are they electrons? You know?
Wow, yeah. Interesting.
Or like, I don't know, like neutrons, protons, negative something.
Yeah, that is interesting.
And the in neutron always tricks me. I'm like protons positive, neutrons negative, and then I'm like, wait, no, that's not right.
Right.
But it just rolls off the tongue, you know. So that's always made me a little bit mad.
Yeah.
Anywho, so that's my little sidebar. So most atoms, yes, consist of those three things. The number of neutrons can change.
Okay.
And the molecules, or the atom will still stay neutral. And that's called an isotope. So if you've ever heard of isotopes before, it's an atom like, say, helium has, I'll just say it's an atom that maybe has different numbering of neutrons present. And so they call that isotope, but it's still considered the same atom. Like,
got it.
If it has different numbers of neutrons.
Okay.
Still considered the same atom. And then electrons we talk about all the time. Electrons are like just going crazy. They're interacting with things. They make bonds when they make things attracted to each other. A lot of times where there'll be like excess electrons over here, and electrons are moving all the time, and you can gain and lose electrons, and all it does is change the charge of your atom.
Right.
And then protons, I feel like, are kind of the main identity of the atom. So protons, you can't change the number of protons without changing which atom it would be on, like which element on the periodic table it would be.
Right.
So that's kind of the basics of atoms. Hydrogen is special though. Because hydrogen, do you know why hydrogen's special? I think we talked about it on the episode on baking soda versus baking powder, but that was a long time ago.
I don't know if I know why it's special, other than that. I mean, maybe it'll be like, oh, we have thought about that as soon as you say it, but I don't know.
Hydrogen doesn't have neutrons.
Oh.
Hydrogen is just a proton and an electron.
Weird.
Is weird. There's isotopes of hydrogen where, for example, like deuterium has 1 neutron and tritium has 2 neutrons. So those are isotopes of hydrogen. And then there's the hydrogen that only has 1 proton, 1 electron.
Can you remember the name of what things are when they have different electrons? Same element but different electrons?
Ions.
Ions, that's right.
Yeah, sorry.
As soon as you said isotopes earlier, and I was like, wait, what's the other one though? Whenever the electrons are different?
That was a good question.
And then I forgot. So, okay, ions.
Yeah, if it's positively charged, it's a cation because cats have paws.
Right.
And if it's negatively charged, it's an anion. And I don't have a good way to remember that.
Because ants don't
have, the ants are negative.
Right. Yeah. Most situations we don't like them.
I mean, but they probably delicately contribute or carefully contribute to the delicate balanced ecosystem.
That's true.
I often wonder about like, what if we just, somebody asked once, what if we got rid of all mosquitoes for the podcast? I was like, probably something bad, although I wish we could get rid of them.
Yeah.
Okay, so that's why hydrogen is special, is because it is just 1 proton and 1 electron. And that means if hydrogen loses its electron and becomes a cation, because if you lost an electron, you're positive, that means it's just literally that the cation of hydrogen is just a proton floating around.
Right.
So the way I think of it is like most times, you could think of atoms, like us having kind of a core, and there's positive and neutral particles, subatomic particles there, and then surrounded by this cloud of electrons, and the electrons can kind of do what they want, whatever. And then if you lose electrons, then you become positively charged. If you gain them, you become negatively charged. But the protons don't really move.
Right.
So the idea that instead of at the core there being like several, protons, really all that's happening in a hydrogen atom is it's like 1 proton with one electron hanging out around it.
Right.
And that's actually why the Bohr model of the atom works well only for hydrogen. Because once more electrons come into play, it starts to get a lot more confusing. And
Right.
So, but that is the Bohr model of the atom is actually good for hydrogen. So you can kind of picture that in your head of like, that's the one like on Big Bang Theory, where they have like one thing in the center and then like a quote unquote electron circling around it on like those little tracks.
Right. I think I know about. I haven't seen Big Bang Theory, but I know that classic image that you're talking about.
Yeah, that's like the classic image, I would say. So then hydrogen, is just when it loses its electron, it's just a little proton and nothing circling it. So that's kind of weird,
That is weird.
And actually, there's a whole area of chemistry, of acid-base chemistry, that defines acids and bases around those protons, around those positively charged hydrogens, which are basically just one single proton floating around.
Interesting.
And that is the most basic definition for an acid and a base that you probably did learn in high school chemistry. And it's that an acid is willing to give up a hydrogen plus a hydrogen cation, also known as just a proton.
Okay.
And a base is able to accept a proton. It's able to accept an H plus.
Right.
And that is the most sort of basic definition of acids and bases that we learn first before we learn any other definition of them.
Okay.
So, in chemistry, an acid can give up a hydrogen, but that acid will usually keep the electrons, making it negative after it's given up the hydrogen.
Okay.
Unless it was positive to begin with, then it becomes neutral. So it becomes more negative when it gives up its proton. It keeps the electrons.
Okay.
And a base will usually accept the proton. So we'll have an excess of electrons, usually negative, but sometimes I guess it can be neutral, and it will accept that proton and become more positive or less negative.
Right. Okay. This is always kind of interesting to me because I think for some reason, the way I think about acids and bases, this is counter what I would expect for some reason.
Okay.
I don't know why, but like I would assume that the acid is already negative, but it's actually the opposite. It's got this abundance of positivity, correct? That it really wants and needs some electrons to balance it out.
Yes.
It's ready to accept them. And for some reason, I always have to really stop and make myself think about that consciously.
I bet it's because there's another definition that you also learned in high school chemistry called the Lewis acid and base definition. And it's like the Lewis acid is an electron acceptor. So I bet you mixed up the proton and electron and what's accepting and what's giving.
Well, I don't even, and maybe I did learn that. I just forgot it. But there's something about the way I think about acids and like battery acid and just things like that makes me think, oh, it's probably like real negative and stuff,
Probably because also it's caustic. It's like burning stuff. But bases are caustic too. So
yeah. And you've balanced that out. And also I think it's just that most of us feel more familiar with acids than bases anyway.
Yeah.
So, at least we think that. But
yeah, isn't that weird? I feel like people know what an acid is, but people don't know what a base is.
Yeah.
So like if I'm like, oh, that's really acidic, that's scarier than being really basic kind of.
Yeah.
Yeah. I don't know.
It's weird. But anyway.
But bases are just as scary, people. Just so you know.
It's helpful to have that rehashed because it's, like I said, it's counter what my brain wants to think for some reason.
Yeah. Acids are willing to give up a proton and they'll be okay once they've given up that hydrogen and kept its electrons behind. And bases are willing to accept the proton. And I like to think of it as like, it's not like you're an acid or you're not. It's really more like on a sliding scale, like how willing are you to give up this proton?
Right.
Are you going to be okay once it's gone? Like it sort of has to do with like wealth and stability in my mind. Like, are you able to give up $50 and it not really affect you because you have all these other like sources of income or whatever that'll keep you stable? If there's other places you can distribute the leftover electrons, if you have these certain features of a molecule that will be able to support what's left over when the proton leaves,
right,
that makes it more acidic.
Okay.
And you can be really acidic where you're really willing to give up a hydrogen or a hydrogen cation or a proton where you'll be more stable once it's gone. Or all the way on the other end, you can be very basic where you don't have a proton to give up, like losing a proton would make you so incredibly unstable, it's nearly impossible. So I kind of think of it on that scale.
Okay.
And it's like a willingness to give up or take. And there are weaker acids that, you know, they can give it up, but maybe they'd prefer not to. And then there's stronger acids, which are like really willing to get rid of their proton. And same thing with bases. They're really willing to accept or less willing to accept.
Okay.
Okay. And you're probably like, what does all this have to do with smells? Because at the point that I was writing this, I forgot that that's even where we were going. I was like preparing this episode and thinking, wait, why am I talking about this?
Yeah, I guess I'm not getting the smells connection yet either, which probably makes sense. It's probably not intuitive until you make the connection for me.
Yeah, it's on its way. Don't worry.
Okay, all right.
Okay. So that's a little bit about what an atom is like, what acids and bases are. And I guess I talk about atoms and protons at the individual level, but molecules are collections of atoms that are willing to give up, you know, one of those hydrogens as a proton, rather than like thinking of an atom giving up its proton. It doesn't do that. It gives it up in the form, a collection of atoms gives up a proton in the form of a hydrogen plus cation is kind of how it's represented in chemistry.
And is it possible for that to all happen and it be not hydrogen?
So that's where the different definition of acids come in, where it's like something can accept electrons and it have no hydrogens, but that's considered a type of acid. So it's missing electrons that it wants or can take on, but it's not really in the form of a hydrogen.
Right.
So a really good example of that is like a pretty strong Lewis acid is called aluminum trichloride. And just the way that the molecule is the aluminum only has 6 electrons around it, but it wants 8. But technically it's all neutral. It just doesn't have the right number of electrons to fill that outer shell, which is a whole other episode and kind of down a rabbit hole. So this is confusing. You don't have to worry about it.
Yeah.
But that type of acid wants electrons, but it's not producing a proton, if that makes sense.
That makes sense. I think my question, the reason that was in my mind, I'm glad we at least touched on it for a second, was me thinking this is so specific to hydrogens, but I was like, surely there's a lot of situations where actually it's not hydrogen at play, but there's still an acid.
Yes.
But in this case, we're talking about hydrogen, and this one
we're talking about acids defined by hydrogens.
Got it. Okay.
And because there's no other way to give up a proton, because if you give up a proton, it would change the nature of the individual atom.
Right.
So when you're giving up protons, that's a hydrogen.
Right. You're giving up a hydrogen atom
minus its electron.
Minus its electron. Yep. Okay.
And that's the definition of an acid we're talking about today. So if that sidebar was confusing, that was a good question. So for other people wondering it, I'm glad we answered. But if that sidebar was confusing, you can ignore it because it was about a different type of acid.
Yeah, I think for me and maybe a couple of people, it's like the idea of thinking about acids specifically revolving around hydrogen only seems like, I don't know all the acids that are out there, but surely they're not all specifically revolving around hydrogen.
Lewis agreed with you. That's why we have Lewis acid.
Nice. Thank you, Lewis. I just, we were on the same wavelength.
Right.
You know?
Yeah, definitely.
I mean, you had to figure it out. I don't know how to figure it out, but you had the same hypothesis that surely it's not all hydrogen.
Surely. I actually don't know if Lewis, what his first name is. I'm assuming it's a person, but I should probably know that. I don't have the history of chemistry just right in my head.
Yeah.
Okay, so back to our smells and our baking soda.
Okay.
We have always said baking soda is a base. And baking soda is, it's got a positive charged sodium, but then it's also negatively charged. So if you kind of think of separating out, you know how in salt you have like NaCl?
Yes.
Really, it's Na plus and Cl minus, and they just hang out near each other because one's positive and one's negative.
Okay.
So similarly, in baking soda, you have Na plus, like a positive sodium. That's why it's baking soda.
Got it.
And then the other part of it is a hydrogen carbonate. So there's H and then CO3.
Okay.
And that is negatively charged. So that's why it has a sodium with it.
Got it.
So that's baking soda. And baking soda is kind of in a family.
Okay.
So think about just the CO3 unit. So we've talked about this a lot. This is a carbonate ion.
Okay.
So it's CO3 2 minus. So it has 2 extra electrons. And sometimes we counterbalance those out with a positively charged ion like sodium plus.
Mm-hmm.
And we just put 2 around there. Sometimes it accepts a proton. So it can have 1 hydrogen and 1 sodium.
Okay.
And then that balances out the 2 negative charges. Or sometimes it has 2 hydrogens.
Okay.
So you have this unit, this carbonate unit that has 2 negative charges, and it wants 2 positive charges.
Okay.
Okay. So sodium carbonate, the very basic one, CO3 2 minus, usually has 2 sodiums around it.
Okay.
It's in a salt form. It's very basic.
Okay.
It reacts very strongly to get a proton.
Okay.
And when it does gain a proton, it now is called sodium bicarbonate or sodium hydrogen carbonate.
Okay.
So there's 1 sodium still counteracting the negative charge, and 1 proton has been added to the molecule.
Okay.
That's baking soda.
Okay.
Okay, so one of the sodium's been basically replaced by hydrogen.
Okay.
And then if you keep going and you add another hydrogen to it, now there's 2 hydrogens around this like kind of core CO3 unit. And it's now neutral, and it's called carbonic acid.
Right. And that is in our sodas.
Yep, that's right. That's in our sodas.
That's one of the the episodes that we have done that has come up in conversation a ton.
Yes.
So that one's, at least some of that is fresh.
Yeah.
Okay.
And it very quickly will break down into water and carbon dioxide because it's not really a happy molecule.
Right.
And that's actually why it's called acid. It's neutral, but it's willing to give up a proton because it's not the happiest acid.
Got it. Okay.
You know, it's like it'll quickly break down. It basically won't stay carbonic acid as long as possible. It's like as quickly as I can, I won't be carbonic acid anymore.
Okay. Got it.
Okay, so that's kind of like if you want to think of it as stair steps or a family, the CO3 2 minus, HCO3 with 1 minus, and then H2CO3 neutral.
Okay.
So they kind of are in increasing stair steps.
Okay.
The one in the middle, that's baking soda.
Okay.
Okay. If it gains a proton, it becomes carbonic acid.
Okay.
Which then breaks down into CO2 and water. And that's why it will react with an acid to make the volcano.
Right. Right.
And that's why it will react with an acid to make the volcano.
Right. Right.
It just does all the bubbles.
Okay.
But it can also lose but it can also lose a proton and go down on the stair steps.
Oh, right. And become even more basic?
And become even more basic and become that CO3 2 minus. It goes from having 1 hydrogen or 1 proton to having none. Okay. And we don't talk about that aspect of baking soda very often.
Right. And for good reason.
Because it doesn't happen very often. For good reason, yes. Because
we're not allowed to talk about that.
It's just usually doesn't do that because it's interacting with acids a lot more in our day-to-day life.
Right.
So we don't spend a lot of time seeing baking soda act as an acid. It would have to be paired with an even stronger base for it to act as an acid and give up that hydrogen that it's just 1.
Oh, I see. Okay.
Okay. So if you put baking soda with an acid, it acts as a base. And it will take that extra proton from the acid.
Got it.
But if you put baking soda with a stronger base, it will act as an acid and give up its extra proton and go back to having no protons.
Got it. Okay.
So it's kind of like it has no protons, and then it has 1, and then it has 2, and baking soda is just in the middle with 1. So it can add 1 or subtract 1. It can go up a step or down a step.
And as it is right now, in its state before you've added anything to it, it's content to stay in the place it's in. But as soon as you introduce other things to it, either an acid or a stronger base, it will go one direction or the other.
Yes. To
interact with whatever it's being presented with.
Yeah, and it's content to be in the state it's in because there's a sodium ion near it that's also hanging out.
Got it. Has anyone made a joke in chemistry about baking soda being base and calling it basing soda? or something like that. It's like not really a pun, but it could kind of help you remember it.
No, I mean, not that I know of.
Okay.
But I will say that the like sodium that's just like by it, that's just like helping it out, is called a spectator ion. Like it doesn't really participate in much that's happening, and it will eventually find another ion that's oppositely charged it, and everything will kind of even out. And so it's just like a spectator. It's not really involved in
Interesting.
I know. It just hangs out. I also think that sodium bicarbonate is a really confusing name because it's only one sodium.
Okay, right.
So I don't know why there's a bi there. I bet somebody will be able to tell me. I'm like, I don't know why it's called sodium bicarbonate and the one with two sodiums is just called sodium carbonate. That's a confusing thing in chemistry that has always bothered me.
Yeah, weird.
I'm sure there's a good reason, but I can't think of it right now.
And if it's confusing to a chemist, can you imagine how confused I am?
Well, to be fair, it's been confusing to me since I was in high school. I remember first learning this and being like, this makes me mad. And I've never satisfactorily found a way to reverse the anger, which means it's persisted.
Is the bi referring to anything else? There's a two something else specifically that there's not two of in the other one? That's so strange.
I don't think so, because it's just one hydrogen and one carbonate unit. Maybe.
That's so weird.
Maybe.
Man,
I should probably know, but just for the record, I teach organic chemistry. I don't teach general or inorganic chemistry. So honestly, sodium bicarbonate does not come up a lot.
Right. Any
sodium carbonates don't come up a lot. Anyway, back to the main event.
Yes.
This was a little what are those called? A side tangent.
Yeah.
Side quest.
Right.
Okay, so you're probably still wondering.
Yeah.
What does this have to do with smells?
Yeah. Are all our smells basic or are all our smells acidic? It's like, what's the deal here? What's going on with these smells?
Well, often when foods begin to spoil, they do emit volatile organic compounds.
Right.
Which are either acidic or basic.
Okay.
There are both. And for reference, I looked up cigarette smoke, if that was acidic or basic, and it depends on the way the tobacco is cured.
Huh.
Fascinating, right?
Yeah, it's weird that it would be that different.
Mm-hmm.
Huh.
So what baking soda does is it can react with the acids and then change them into something else that isn't as smelly, or it can react with strong bases that are stronger bases than itself that are going to steal its proton that it has.
Right.
And make them less smelly than they were before.
Right.
It literally can do both. And that property of being considered acid or base, or like being able to act differently in different situations, is called amphoteric.
Amphoteric.
And so baking soda, because it's amphoteric, it can literally neutralize. It doesn't really trap, as far as I know, like on the episode we did with odor eliminators.
Oh, right.
Where it literally is trapping those molecules. It doesn't trap them. It neutralizes them by literally reacting with them.
Got it.
If they're acidic, it acts as a base. If they're basic, it acts as an acid, and fundamentally changes that molecule so that it no longer has those really acrid smells.
Got it.
And that's how baking soda acts as an odor eliminator.
Wow, interesting. I'm guessing there are probably some smells that like you could react with them and you take some electrons away or add some or whatever. There may still be a smell, but it's probably going to make a difference of some sort.
Right. And it also has to come, if you think about it at the molecular level. So like imagine being a tiny person inside your fridge. But don't actually get inside your fridge because you could suffocate because it's an airtight. Right.
Okay. So be a tiny person, but don't get in my fridge.
Yeah. Especially if there's kids listening. That my mom used to really freak me out about that.
Oh, yeah. I remember my mom too, because there were so many stories when I was a kid of like that happening.
Yeah. Especially they would like in like junkyards and stuff. Kids would go play in like abandoned.
Yeah.
Like somebody just tossed their refrigerator out.
Yeah.
So if there's kids listening, don't do that. But imagine yourself as a tiny person inside your fridge. It's an enclosed space. And if you could see the molecules in the air, they're really, really tiny, but they're all just moving around in there. And in order for the reaction to happen, the volatile organic compound literally has to come into contact with the baking soda. And so that's not happening just all the time.
Right.
So there may still be a little bit of a smell, but it is likely still neutralizing. So I would think it would work best actually if you had it like in a shallow dish on several shelves. But is it practical to have a bunch of open shelves of baking powder? Probably not.
Probably not.
But so that's part of it is there may be smells that interact with it and stay a little bit smelly, or maybe not all the molecules are going to come into contact with the baking soda.
Right.
But what it does come into contact with, it should neutralize.
Okay.
Okay.
Okay, I think I get it.
All right. Do you want to take a stab at it?
Yes. I think the hardest part for me is going to be the structure, which I'm guessing you don't really need me to say all that back, but remembering that molecular structure and how it can change, that's so hard for me.
Okay, let me help you.
And I also thought there's like very rare times, if you're a listener out there, I don't ever take notes in this
Oh yeah.
show. That was one of those times where like that happens every so often. I'm like, ooh man, taking some notes would super help. Just in this scenario where I'm just listening audibly only and no visual, or trying to create my own visual while we're going, which is kind of challenging.
I think I have a way that I can help you.
Okay.
Do you want me to give it to you?
Yes.
Okay, so you can imagine the carbonate, the CO3 with 2 negative charges, like a Mickey Mouse head.
Okay.
So imagine a Mickey Mouse head, and it's got its 2 little ears. And if you took those ears each off and it left behind a negative charge, it would want a positive charge, or like it would, want a positive charge to come back and neutralize it.
Okay.
So it wants its Mickey Mouse ears back.
Right.
So sodium carbonate has no Mickey Mouse ears. CO3 2 minus. Baking soda in the middle has 1 ear.
Okay.
And then the carbonic acid has both ears. It's actually not very stable in that form either. But
right.
So the one with only 1 Mickey Mouse ear can either go up and have both of its ears, or it could go down and have neither of its ears and just be a circle.
Okay.
Does that help?
Yes, kind of.
It's like it's missing 2 things.
Yeah.
And it will eventually gain both of them, but while it's in that intermediate state, it could gain one or lose one.
Got it.
If a bigger bully, if someone who's stronger comes along, is like, that's my Mickey Mouse here and I'm missing one too, it'll just rip it right off.
Yeah.
But if someone that the Mickey Mouse original guy could bully comes along, he's like, now I'm going to get my second Mickey Mouse here. It's just a bunch of violent bullies in the acid-based community.
It's intense in there.
Okay, so that's my very brief analogy. I want to hear you explain it back, because I do think this is one of the most abstract concepts we've done. I remember feeling that way when we first talked about baking soda.
Yeah.
And so we're revisiting it now. Maybe I'm better 4 years down the line.
Here's one thing that's come to my mind a little bit that might help at least me understand. Even if it's not a better analogy than what you already did. But it's just, what if you're somebody and you have 1 shoe?
Okay.
And you don't really need 1 shoe, right? So honestly, if you got the 1 shoe, you're okay to sell it. You're down to sell the shoe. I was thinking about this because I was looking at secondhand clothes the other day online. And there actually are times where you'll find just 1 shoe for sale. I saw it actually several times. Usually it's because somebody only needed 1 because they had to buy one for their prosthetic.
Oh, yeah,
yeah. Or for their foot that doesn't wear that isn't prosthetic.
Yeah.
Anyway, long story. But so you got the 1 shoe. You don't need 1 shoe, most of us. So you're willing to part with it and sell it. Or if somebody came along and actually have the other shoe.
Yeah.
Then your situation changes and you're actually willing to take on that other shoe.
Yep.
But as it is with just the 1 shoe, you kind of would rather have not the shoe at all, or both.
Yep.
And so baking soda finds itself in the place with the structure that it has of being of 1 shoe. And if an acid comes along, it's willing to give up the shoe in that case?
Close.
Dang it.
Acids.
I knew I was going to get mixed up on that.
Acids give the protons. So acids give the shoes.
Okay, right. Because the proton is changing hands here.
Yes.
So the hydrogen that doesn't have an electron is moving from one place to another.
Yep.
So it's taking on the shoe.
Uh-huh.
If it interacts with an acid.
Yes.
And if it interacts with a base that's stronger than it, then it gives up the shoe. Mm-hmm. And from there, in the case of, this is a perfect situation in the case of smells and odors, because they can be either acidic or basic, depending on the odor and smell, the volatile organic compounds. And so then it's great that baking soda can go either direction with its shoe situation. It probably doesn't cover all odors perfectly, but it makes it much more versatile than maybe just any other old base that you could find to put in your fridge.
That's a really good analogy. I'm going to expand on it a little.
Okay.
Because I feel like there's some subtleties that didn't quite get captured, and this is a good analogy to do it.
Okay.
I think that if you have one shoe, in the case of baking soda, it would rather have two than have none. Okay. So it does more easily accept a shoe than give up that shoe. So maybe it's outside and it's, in the summer in Texas, it's pretty hot on the concrete. So maybe it's like, it would be better if I had two shoes.
Yeah.
But if a stronger base comes along, like a bully, he's like, fine, man, take my other shoe. It's not that big of a deal. I just walk in the grass.
Yep. Yeah.
But really,
I don't want any trouble. Here's the shoe.
Yeah. Yes. But really, you'd rather have two shoes in the summer in Texas.
Right. And even in any scenario, if the other option is zero shoes, you probably would always prefer two shoes.
Yeah.
Yeah.
So, but it is okay with one shoe. And I can't figure out a good reason in the analogy that we're fine with one shoe.
Yeah.
Maybe he has fashioned some sort of shoe out of sodium, a salt shoe.
Or like, I think if I had just one shoe, I think I'd kind of be like, I'm going to just throw this away, right?
Yeah.
It's perfectly good shoe.
Yeah.
I'm not going to throw it away. I'll hang on to it.
And maybe I'll find...
If I find somebody who needs this other shoe, great, cool. Mm-hmm. But if I find the other shoe that matches this one, best scenario.
Yeah. I think it is kind of like that.
Perfectly good shoe. I love the shoe.
Yeah.
Love it. Okay.
And there is a way that you can just put baking soda on on a baking sheet and bake it at 400 degrees and it will react with itself to make the no shoes situation. It'll make sodium carbonates.
Interesting.
Yeah, if you give it enough heat. So it really needs energy to get to that. Yeah. It doesn't want that.
Yeah.
But so I thought that was a very little interesting thing. And I hadn't really thought about why we put baking soda in our fridge until today.
Yeah. Interesting.
So that was a fun little trip down. Why do we do this lane? Speaking of fun trips, I'm going to usurp you. And instead of asking you a question first, I'm going to say that I took a fun trip this weekend.
You did. And it's okay for you to usurp because I'm not in a position of any sort of power or dominion over the situation. And I welcome your sharing of your story of your trip.
Okay. So this is transitioning into our happy time. I took a trip this weekend it was me and my husband and two of our friends. And we went to Mexico City. And then we traveled from Mexico City. We did a day trip and saw the monarch butterfly migration.
Nice.
And it was insane. It was so cool. I really appreciated it. And my friend, y'all know my friend because she's come on the show. Mm-hmm. Friend of the show, guest expert, Vianette. She is originally from Mexico. And so she was sharing about her culture. And it was so fun to get to participate in her culture and to be in a different country. And it was only a 2.5 hour plane ride, which is less time than it takes to drive to most places in Texas.
Yeah, so. Yeah, 100%.
And the food was delicious. It was so fun. And so I had a really good trip this weekend, and that's my fun thing.
That's awesome.
I also am going to break the rules and say another fun thing.
Okay.
Just because.
We'll see.
Just because I want to.
Go ahead and say it, and then if I don't like it, I'll just cut it out.
Yeah, that's true. You really do have all the power in this situation.
I'm just kidding.
I'm like, add that back in. He's like, no. Yeah. And I have no recourse to add it back.
I really could make you sound horrible.
Yeah.
And I could make
and wrong and dumb.
Yep, I could make all your signs not make any sense.
Yeah.
I really wanted to.
That's true. You really could.
But sorry, go ahead.
So also a little bit of exciting news today. My paper that I wrote in a peer-reviewed journal during my dissertation work during my PhD was officially published.
Yes.
And it was published in the Royal Society of Chemistry magazine, Chemistry Education, Research, and Practice. And they have worked with us as sponsors for the show before.
That's
and
right.
They have other really good podcast called Chemistry World, where it kind of goes in depth on different molecules. So that was fun and cool and a great connection.
That is awesome. Dang it. Both those things are super cool.
Yeah, sorry.
That's
I was
okay.
like, I can't pick one, so I'm just going to give both.
That's totally fine. And also, our friends with that you went to see the Monarch Butterflies with, they've gone many times. Every time, always amazing pictures, amazing videos, all that kind of stuff. So I'm jealous you got to do that. I'm never going to forgive you.
That's okay. Once your kids get older, I feel like that would be a doable trip with kids, actually.
Oh, totally.
And be really, really cool.
Yeah. I mean, that 2.5 hour plane ride sounds like amazing. I mean, it sounds...
The hardest part is it was a 3-hour drive to the sanctuary where the butterflies are, but you can get like a charter bus.
Right.
And then, kids think buses are cool.
Oh, yeah. Yeah.
So,
100%.
I think that would be a doable trip with kids.
Yeah.
And
noted. That's a good point.
It's amazing.
And then I'll forgive you once I've been there and I've seen it.
It's okay. You can hold that grudge against me. It was way worth it.
Okay, mine is a lot less cool than both your things. So we knew that going in. We knew that after you said yours.
Yeah, maybe I should have let you go first so I didn't,
It's okay. I mean, yours were more exciting, and so you wanted to get them out and make more sense.
It was so hard to hold them in.
So mine is simply that. I think I want to say I talked on the podcast, and we'll share one of these, that I'd started baking some banana muffins again, banana bread muffins.
Yes.
Recently.
And I was supposed to send you the blueberry muffin recipe, and I never did.
Yep. And another reason, just add that to the pile of things, grudges to hold against you.
It's rude.
So send that to me. But what I did do the other day, I was just curious. I was like, I wonder if I have all the things to make chocolate chip cookies from scratch, which I've never done before. I know
You've never done before?
No, and I know it's not that hard, but I'd never been curious enough.
Listen, I'm not going to shame you for it. I'm just saying that's exciting that you're talking about doing something you've never done before. That's like not every day.
I know. And I found a recipe that was the easiest one. It was even called like the easiest chocolate chip recipe ever, chocolate chip cookie recipe
I feel like
ever.
The Nestle one is a go-to.
So I looked at it and it was all easy. Didn't need to have a mixer. I don't know what the variety of different recipes for chocolate chip cookies are, but this one was super simple. Nice. And I did it so fast and didn't even tell him what I was doing. And just like went over there, I think we were watching a show and I like whipped this up together super quickly. Probably the longest thing that took was just melting some butter. But that was it. And then threw it in, didn't tell her Em loves surprises. So I even small things like this like to make surprises. And then I just pulled out this cast iron chocolate chip cookie thing that I had made from scratch. And she was like, I didn't think we had any cookie dough. I was like, I know. I just made it.
Oh my gosh. Was she so excited?
Yes, she was. And it was quite good. So
did you eat it with some ice cream?
Oh, yeah. 100%.
Nice.
So
I love that.
That was really fun. And I was like, okay, I've always said I'm not like huge into baking. I like cooking more than I like baking.
Yeah.
But, this is just the toe in the water thing.
Yeah.
The muffins are the gateway into like, oh, wait, what about chocolate chip cookies? What about this? What about that? And here I am making stuff like that and looking for excuses to bake other things.
Yeah.
So who am I?
Who are you? That's exciting. I think that's more exciting for me than you realize. I'm really excited about that. I also recently made chocolate chip cookies for a party, like a girls' weekend I was going on. And I made them from scratch, which normally I just get the Nestle cookie dough because it's so easy. But I made some because it was cheaper.
Yeah.
Because eggs are, even with eggs being expensive, everything has gotten more
Totally.
expensive. And it was actually really surprisingly quick. And I thought, why don't I do this more often?
Totally. And I've been replacing the eggs because my son is allergic to eggs, even though actually most things that are cooked really well, it doesn't actually matter or affect him.
Yeah, like baked goods. Yeah.
Usually it's not a problem. But the eggs being expensive, I've been using applesauce instead.
Oh, yeah. I've heard that's good.
And on topic, actually, I found an article that talked about how applesauce changes the consistency just a little bit. and it makes it more dense. And so they say to add a little bit of baking powder.
Just a little extra to lighten it up.
Lighten up a little bit so it can kind of create a little bit more air pockets than what
what's naturally in there.
Yeah, and what you'd need if you just did egg instead of applesauce.
Yeah, that makes sense.
So anyway, that's been some chemistry at play there.
How fun.
In the baking. Obviously, there's tons of chemistry at play, but
Well, that's a good one. Thanks, Jam. Thanks for telling me your baking hacks. I will always go baking, and I'm so excited that you're finally getting into the world of baking with me.
Me too.
It was a matter of time. I already sent you the blueberry recipe, so you can do that.
Excellent.
And thanks to all of you listeners, and a special thanks to listener Katie Jordan, who asked me about baking soda today, which kind of got my mind going down this path. So she didn't ask the question specifically, but just asked a different chemistry question that got the wheels turning. So thanks, Katie. Thanks, Jam. Thanks to all of our listeners for learning about the chemistry of baking soda.
And thank you for teaching us. And if you have questions or ideas, things you wonder about if they're chemistry in your everyday life, please reach out to us on our website at chemforyourlife.com. That's chem, F-O-R, yourlife.com to share your thoughts and ideas. If you'd like to help us keep our show going and contribute to cover the costs of making it, go to patreon.com/chemforyourlife or tap the link in our show notes to join our super cool community of patrons. If you're not able to do that, you can still help us by subscribing on your favorite podcast app and rating and writing a review on Apple Podcasts. That also helps us share chemistry with even more people.
This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson. Jam Robinson is our producer, and this episode was made possible by our financial supporters over on Patreon. It means so much to us that you want to help make chemistry accessible to even more people. Those supporters are Avishai B., Bree M., Brian K., Chris and Claire S., Chelsea B., Derek L., Emerson W., Hunter R., Jacob T., Christina G., Lynn S., Melissa P., Nicole C., Stephen B., Shadow, Suzanne S., Sam N., Stephen B., Timothy P., and Venus R. Thanks again for everything you do to make Chemistry for Your Life happen.
Hey, we'd also like to give a special thanks to our team of reviewers who reviewed this episode. And if you'd like to learn more about today's chemistry lesson, check out the references for this episode in our show notes or on our website.